This video presents some details that I never go over in class, but does so in a rather quick fashion. That way all of you can gain an overview of the main principles that underlie the ideal gas model, while those who want to gain a deeper understanding can pause the video as needed. The first distinction I want to make is between a law, as you've probably encountered it in other classes, and the model that we're using here. The ideal gas law is not actually the law. It's actually an empirical relationship that on average, like a least squares fit to data, describes experiments done with various gases in the laboratory. It does not always give correct answers. There are some experimental areas where it does not work. It does work extremely well, however, under the normal conditions that we see in this class. That makes it extremely useful and valuable. The problem with a law is that it's limited to giving back what you put into it. It's simply an empirical relationship from experiment. For example, this law cannot be used to answer a different question, such as how much energy you need to add to a gas to increase its temperature by 1 degree Celsius. In contrast, the kinetic theory for an ideal gas is what we call a model. It's based on mechanics and statistics, which is why the field is called statistical mechanics, plus some assumptions about atoms that were made at a time when there was no experimental evidence that atoms even existed. Today we can justify most of those assumptions and understand exactly when they're valid and what their limitations are, so this model is a lot stronger today than it was at the time it was proposed. Now, models typically have parameters, usually ones that are found experimentally. However, what gives them an advantage over a simple fit to data like PV equals nRT is that a model can be used to make additional predictions because the underlying mathematical structure of the model means that more than one result is related to that one parameter. In this case, the kinetic theory of an ideal gas can predict how much energy you need to add to a gas to increase its temperature by 1 degree. The assumptions of this model have been mentioned before. Matter is made up of atoms that interact via forces, and the collisions in particular are going to conserve energy and momentum. Motion is random, involving a very large number of atoms, and because the number of atoms participated in solving Newton's law's equations is so big, because that number is so large, we use statistics to calculate average values rather than trying to solve the equations. Now, the assumptions, to state them a little bit more carefully, are that the atoms and molecules are extremely small compared to the distances between them in a gas. That is, they move rather freely and have only rare collisions with other molecules. There are no long-range forces at all. Short-range forces are limited to interactions during elastic collisions. As a result, the idea that a gas could condense to a liquid is not allowed within this model. And finally, we use Newton's laws for the collisions. Now, I'm going to restrict my analysis here to monatomic gases, to noble gases like helium or neon or argon. So you might ask, can we go beyond these assumptions? The answer is yes. The model itself includes diatomic gases and more complicated molecules. I just don't want to spend time on that. Plus, the model can be extended beyond the assumptions we make here to include the effect of short-range forces and the size of molecules, especially as they show up in a dense gas. So, the starting point is something you've also seen before. Temperature is determined by the average translational kinetic energy of an atom in the gas. Another way of saying this is that kinetic energy is what makes things hot. When the temperature is 0, the average kinetic energy is 0, and that means the velocities of all of the atoms is 0. They are at absolute rest, which is what we mean by absolute zero. Now, this is only true in the classical statistical mechanics that we're looking at here. In quantum statistical mechanics, that's changed a little bit. But this is enough for us to understand what we need to understand here. That temperature is, of course, the absolute temperature in Kelvin, and that K is our single parameter of the model, the parameter that's called Boltzmann's constant. So our picture here is that when we've got a cool gas, the atoms are moving relatively slowly. When we have a hot gas, they're moving faster. And that additional kinetic energy is what we mean when we say something is hot. It's got a lot of kinetic energy. The molecules collide with each other and with the walls of the container. The collisions with the walls of the container are the result of forces, and those forces result in what we call pressure. So let's look at what happens when those atoms collide with the walls of a container. And here's our sample container taken from a figure in the textbook. It's got a length L, a width W, and a height H. And you see all those little circles which indicate atoms that are bouncing around inside. They're moving at random in that rectangular container. Because they're at random locations and in random directions, we only have to look at what happens at one wall. Every other wall looks exactly the same. So we're going to focus our attention on the wall at x equals L, which has an area W times h. At that wall, a single atom is going to be moving with a velocity with x, y, and z components. We only see two of them here. And when it bounces off the wall, only the x component will change. The y component will not change because the force of the wall is normal, that is perpendicular to the wall. So what happens is that the momentum in the x direction is changed. As usual, final minus initial gives us negative mvx minus a plus mvx, or negative 2 mvx for the change in momentum. The y and z components of the momentum do not change. That change takes place over a certain amount of time. That time can be determined by the distance that they have to travel. And again, although I'm looking only at the x velocity for the collision, I also only have to look at the x velocity for the time, because the time it takes for the travel of the distance x equals 2L from one end to the other and back depends only on the x component of the velocity. And that x component is going to be 2L divided by delta t, and therefore the time is 2L over the speed. That means the net force on that atom, which is dp dt, is the change in momentum over the change in time, which is going to be negative 2 mvx divided by 2L over vx. The 2's cancel, the vx ends up in the numerator, and we get a result for the force of the wall pushing on the atom. Okay, so what have we got? We've got a force that's negative to the left, required to change the momentum from right to left, and is equal to negative mvx squared over L. What does this do to the wall? Well, the assumption here is that there's an elastic collision with the wall, and in fact that the wall is infinitely massive. This means that the wall does not add or remove any energy from the gas. The wall doesn't get heated up by the gas, and the wall does not add any heat to the gas. Similarly, no work is done on the wall, and no work is done on the gas. For now, what we're doing is we're making assumptions that allow us to completely isolate the gas from the outside world. The first law of thermodynamics will be used to connect what's going on inside the gas to the outside world. Right now we're just looking at the gas. Okay, so what happens to the wall? Well, if the wall pushes on the gas must push on the wall. Newton's third law tells us that the force on the wall will be in the opposite direction, that is plus, and have the same magnitude, mvx squared over L. And of course we know that pressure is force over area, and we know the area is the width times the height. So if we combine these together, we see that that change in momentum results in a force on the wall of mvx squared over L, and a pressure that's going to be that divided by the width times the height. That result, that the pressure on the wall is mv squared over the volume, leads directly to something that's very close to the ideal gas law. And you do see the volume. The L that we needed to calculate this time is multiplies the width and the height for the area. And I'll just point out that if you do the same calculation in other directions, you'll get the same result in a different order. You'll have the width give you the time, and L times h will be the area. So the results for x, y, and z look exactly the same. The pressure on this wall, mvx squared over v, looks exactly like the pressure on some other wall, say mvy squared over v. And the formula PV equals mvx squared is our next starting point in the calculation of what's going to happen. It looks a lot like the ideal gas law. In fact, there's only one more thing left to do. What we have to do now is make explicit use of our assumption that there's a large number of atoms moving randomly and on average sharing equally the energy of the system, while in fact the center of mass is at rest. That is, all of the motion is sort of symmetric and balanced, with as many atoms moving one way as moving another way. But in particular, that the motion in each coordinate direction x, y, and z is sort of equally sharing the energy. This idea is called equipartition, that is, equally divided. The energy is equally divided between all of the different things that that atom can do. So when we look at the kinetic energy, which is 1 m times the quantity Vx squared plus Vy squared plus Vz squared, what that means is that on average, each of those components carries 1/3 of the total. That is, on average, 1/2 mvx squared equals 1/2 mvy squared equals 1/2 mz squared. And that is 1/3 of the average kinetic energy. So if we look at the blue part and just multiply through by 2, we see that mvx squared is 2/3 of the average kinetic energy. But that's 3/2 kT. So when we multiply 2/3 times 3/2, we get just kT. And now I think you can see why that 3/2 was snuck in there in the definition. It slipped into the definition so that this works out nice, neat, and clean. That is, the 3/2 fixes the 2/3 that always happens when you do this calculation. That is done just to make the definition of Boltzmann's constant K the right kind of number to use for other things. Therefore, to summarize, using the definition that the average kinetic energy is 3/2 kT and the equation that the pressure times the volume equals mvx squared that we derive from Newton's second law for the elastic collisions with the wall, and then mvx squared equals kT that we got from that average kinetic energy equation with the equal partition assumption, that gives us PV equals kT for one atom. When there are n atoms, this is just the ideal gas equation, PV equals nkt. And if we replace nk with lowercase nr, PV equals nRT. And of course here we're using the more standard form where we're going to write everything in terms of the gas constant capital R, which is Avogadro's number times K. And in this course we'll use R equals 8.314 joules per mole Kelvin. And this is obtained directly from Boltzmann's constant, which is 1.381 times 10 to the negative 23rd by multiplying by Avogadro's number that you see there, 6022 10 to the 23rd. Okay, so to summarize, our picture here is something that I want to introduce some language we're going to use later, that each of the state variables of the system, the pressure P on the piston, the volume V of the gas, the temperature T of the gas, and the number of molecules are related by this equation PV equals nkt. If you replace the number of molecules by the number of moles, you also have, which is an equivalent state variable, you have PV equals nRT. Now this is a prediction confirmed by experiment that if you'd fit data for P times V versus temperature for an ideal gas, a simple monatomic gas like helium or neon, you will get a straight line with a slope of either K or R depending on what you use for N. And then once we determine that value of K from data, we can use it to make other predictions. Now, those other predictions, like the specific heat for a monatomic or diatomic gas, which we are going to use in this course, or the speed of the gas molecules that one can use to confirm the model, would make this video too long, so I'm going to put them in a separate video. As before, some of these figures have been taken from and in many cases extensively modified from those found in Chapter 17 of our textbook.